All right, good afternoon. Eric, if you want to get us started.
Welcome, everyone. Today, we are pleased to have Trevor Lewis, who will be giving our Oliver Brand Memorial Lecture Series, the GLUE series, Global Lectures Uniting Everyone. Before I turn it over to Stacy, who will introduce our speaker, I want to tell you a little bit about this series. You can go to the next slide. First, this is the Oliver Brand Memorial Series. Oliver was a co-PI for the ACME Center and led our technology core. Oliver received his PhD from ETH Zurich in 1994, was a postdoc at Georgia Tech, and then a lecturer at ETH Zurich, followed by being the deputy director of the Physical Electronics Laboratory. In 2003, he joined electrical and computer engineering at Georgia Tech and was a world-renowned expert in MEMS, microelectromechanical systems technologies. And as I said, he was one of the founders of our ACME Point of Care Technology Center. We have a memorial fund that is set up, an endowment in his memory that's been established at Georgia Tech. And you can either use the QR code here or the link shown to give to that endowment. Next slide. Um, go ahead. So just a little bit about the ACME Center. So the ACME Center is an Atlanta-based team, obviously, between Emory University, Georgia Tech, and the Children's Healthcare of Atlanta. And our primary goal is to assist and enable inventors from across the country who have developed microsystems-based point-of-care technologies and help them to accelerate those to translation and clinical adoption. And so we have an annual call for proposals. We had one that ended just this past spring, and we can fund your research and also provide support. So we have clinical support, we have usability support, technology support, and other types of support to help move your technology forward. Next slide. We are organized into four cores: our administrative core, our technology core, that's led out of Georgia Tech, and we have capabilities in materials characterization and in microsystems fabrication. So we manage a clean room here and can help you, design and prototype your microsystems. Our clinical core, of course, helps with clinical validation testing, feasibility. We can also provide regulatory consulting. We have a biobank of samples that can be used to help you further develop your technology. And then finally, our dissemination core, who helps with training activities, as well as this lecture that we have here today, the GLUE lecture. Next slide. And so with that, I'd like to introduce Stacy Howman, who will introduce our speaker.
Everyone, thank you so much, Eric, for that great overview of ACME POCT. I am Stacy Heilman. I'm a card-carrying and proud member of Core 4, and it gives me great pleasure to introduce today's speaker, Dr. Trevor Lewis, who earned his master's and his bachelor's in IT from the Georgia Southern Polytech University and a PhD in cyber operations from South Dakota State University. He is now a principal research scientist of offensive and defensive cybersecurity engineer and professional education instructor for the Georgia Tech Research Institute, or GTRI, and has been so for the past 10 years. As witty as he is wise, Dr. Lewis has been called an emblem of both expertise and enthusiasm. Reading about his approach and contributions to the field, it has been noted that he tirelessly delves into discovering the unknown problems of the cyber realm, crafting designs for a more secure digital landscape. His expertise and research primarily focus on both offensive and defensive cybersecurity, encompassing areas like penetration testing, red teaming, cyber threat emulation, attack chain development, and exploit development. We are both excited and honored to hear from him on specifically what diagnostic device developers need to know about cybersecurity. He will cover a wide range of topics today, but we plan to leave plenty of time at the end for discussion and questions so we can dig deeper into any of the areas that you want to know most about. So I urge you, as he covers these topics throughout today's talk, please use the Q&A feature during the talk and we will field your questions at the end. Thank you so much, Dr. Lewis. Turning it over to you.
All right. Thank you, Stacy. Let me make sure my mouse works. Yep, looks good. Thank you everyone for having me. Stacy mentioned I'm Trevor, work for the Georgia Tech Research Institute. Put together this brief, kind of to show you my picture of the world, both, in cybersecurity, the threats that we're facing today, especially in the medical field, and tell you what we can do about it. So, Stacy mentioned I'm a principal research scientist at Georgia Tech Research Institute, which is the applied research and development arm of Georgia Tech, the university itself. My PhD in cyber operations, which is a little bit different than your typical focus areas that universities have, but Dakota State University is very DoD aligned with DoD mission sets, and the NSA Centers of Academic Excellence, NSA CAE, cyber operations is a specific designation for focusing on that offensive and defensive cyber operations and exploitation to better secure our systems, really. So, my areas of expertise kind of fall into three areas: the offensive, defensive, and security architecture spaces. So that involves a lot of attacking things, assessing architectures to determine whether or not they are vulnerable to attack, and all of this, of course, to make sure that we identify vulnerabilities, patch them, mitigate them before real cyber attacks happen. And this happens across, all of our portfolio of sponsors. We do sponsored research from federal sponsors to commercial entities, and I'll take you through all of that. Let's see if this is working. Okay, so GTRI, like I mentioned, applied research arm of Georgia Tech. We have 8 laboratories. I'm in the CIPHER lab, the Cybersecurity Information Protection and Hardware Evaluation Research Lab. I give you this context just to emphasize and show you that GTRI is mostly a defense contractor, effectively. All of our labs focus on a lot of DoD mission sets. Most of our funding, it's all externally funded. We're all soft money. Comes from the DoD for a variety of different purposes. And within the cybersecurity lab, the CIPHER lab, it's with DoD sponsors, it's with industry, various critical infrastructure sectors and companies. And to give you kind of an idea, when we start talking about in the future, if you want to partner with us for research, we have field offices all over the country, naturally close to military bases and DoD installations. But we're not just in Atlanta; we're all over the place and can really go anywhere in the country to help and do research. Within the CIPHER lab, our research portfolio kind of encompasses a very wide breadth of areas from your basic research down to quantum computing and sensing. We have a quantum computing group within our laboratory, and they're literally developing the future in physics for quantum computing, all the way to very applied, high TRL level research that I'm more associated with in mission assured command and control, advanced cyberspace operations, resiliency of cyber physical systems, and vulnerability identification in embedded systems. So there's a delay in this clicking. There we go. Our group, we kind of are different than a lot of GTRI. We provide a lot of professional services type um, research to external entities. We're industry certified red teamers, and so that comes with assessing all the different types of systems in DoD, electric power, water, wastewater, healthcare, a lot of other critical infrastructure entities, in IT systems, OT systems, operational technology, if you've heard that term. Identifying those hidden vulnerabilities. We kind of use this cycle. We identify vulnerabilities, but we come up with custom cyber defenses. If your vendor technologies can't or controls that are commercially available can't actually detect or prevent techniques from attackers, we can bolt on to existing cyber operations, defensive cyber operations components, help organizations detect threats. And then we're also professional education instructors for GTPE. So we design and deliver custom professional education classes on a variety of cyber topics to anyone that really needs it. We hold public classes here in Atlanta if you want to attend those, or we have custom ones that can be delivered to organizations directly. In terms of critical infrastructure, I'll talk a lot about that in this because healthcare naturally is a very important piece of the critical infrastructure puzzle. We have direct experience, either personally or through sponsored research, in 11 of the critical infrastructure entities, and we're growing those very rapidly. In terms of the types of systems that we assess, I mentioned that I do penetration testing, red teaming. So that's kind of taking the role of the adversary, the role of the cyber threat, and trying to penetrate, trying to exploit a system to identify holes and be able to mitigate those vulnerabilities and pathways before a real cyber threat finds them. So across all of our sponsored portfolio, we have a wide variety of experience and different types of systems, your traditional enterprise networks and systems, from small businesses all the way up to Fortune 500s. Cyber physical, ICS, industrial control systems is a big piece of what we do. And it gets into the deeper areas of the critical infrastructure area, sectors, and healthcare systems, financial networks and systems, aviation. So it really is a very wide range of types of systems, and that gives us a unique perspective on what the real cyber threats see. If you can step back and look at all the vulnerabilities across different types of systems in different industries, different sectors, that allows you to really kind of understand where the problems lie, because you'll see them repeat across different sectors. You can anticipate and prevent them potentially. So that gives us a unique perspective in the world. Now, I want to kind of use this webinar as also kind of a call to action, because GTRI being a national security aligned entity, we see the problem differently than a lot of other academic research institutions. The threat tactics, techniques, and the intensity and the severity of them against all of our systems, U.S. critical infrastructure, international critical infrastructures, really the cyber warfare landscape is broadening and it is getting more severe. So I'll kind of take you into my perspective into the world, because that directly aligns with the types of systems that you're building, where they'll be plugged into, and how it affects society. So last year, around January 2024, U.S. intelligence community agencies had a hearing with Congress to discuss what they're calling Volt Typhoon, the People's Republic of China. It's a cyber threat group associated with the PRC, and the types of tactics and techniques they're using across the world, not just the U.S., to conduct cyber operations, to attack systems, and what they're calling pre-positioning. This is the most severe part of it. They're pre-positioning in U.S. critical infrastructure to cripple vital assets in preparation for some future event. Now, some of that is not destructive right now, but it is in preparation for being destructive. And that can have huge effects for society. And that's why we need to be aware of it. That was in 2024. This in 2025 on the Congress's website, it says U.S. intelligence community assesses that the PRC is the most active and persistent cyber threat to U.S. institutions. And the Office of National Cyber Director has highlighted that their ambitions are to hold at risk U.S. and allied critical infrastructure to shape decision making in a time of a crisis and use cyber capabilities to augment PRC geopolitical objectives. Unfortunately, that affects all of us, every system, every device, even us personally. Your home routers, your home phones, everything that's connected to the internet nowadays is subject to attack. And so, it by these intelligence agencies coming out and saying this, they are intending to basically compromise everything that they possibly can in the world for their strategic positioning. So the different threats that they've called out: Volt Typhoon, Flax Typhoon, and Salt Typhoon. Over the past couple of years, those have had different angles in attacking various systems. Volt Typhoon being specifically critical infrastructure. That was the one from 2024. Flax Typhoon is interesting because it focuses on Internet of Things devices, which is very important for IoMT, Internet of Medical Things, which we'll talk about. And then Salt Typhoon is the one that's in the news recently about compromising US telecommunications companies and being in there for a very long time. So that's the state of the world in cyber warfare. It becomes more interesting when you combine that with a kinetic type of conflict. And we see that in the Israel-Hamas war and the Russian-Ukraine war, where these adversaries, these cyber threats from nations, will combine their cyber operations with things that they're actually doing in wartime battlefields. So, and the scale and the intensity of them increase, and they'll combine a lot of different things like ransomware, a lot of deceptive tactics to create fear, uncertainty, and doubt in society. So, even if you're away from the battlefield, you could still be affected by it. And this is kind of what we're anticipating in the future. If this ever does happen, these are the types of things that we can expect to be combined with things that happen overseas. And that's one of the points that I want to make. Even if a conflict is in a different part of the world, that doesn't mean that we won't be attacked in other places of the world. That's just the nature of, cyber warfare being interconnected with everything. So we just have to be ready and cognizant of those types of issues, especially for critical infrastructure. And I drew this because, critical infrastructure sectors, they all kind of depend on each other in various ways. I look at it from a public safety perspective because I also have a background in law enforcement a long time ago. So I see those interconnected points, the dependencies between different critical infrastructures, and healthcare, in my opinion, is directly above. If you take tier one as being the most important that everybody kind of depends on, electric and water, healthcare is right above that because in a public safety type of emergency, everybody depends on healthcare to be there, but healthcare depends on a lot of other critical infrastructure entities and very specific things. That's where the directionality of this graph that I drew comes from. They depend on very specific things from different infrastructures. So that's why this is a big problem. That's why we're focusing on it at GTRI to really help prevent cascading effects if there ever is an emergency. Now, let's talk a little bit about how cyber attackers think and operate, because that's going to be important for how you develop your devices, because your devices plug into various networks and systems, and either in healthcare environments or clinics outside of the primary environments, things like that. These are the four echelons that I really kind of categorize different cyber threats. You have your unaware opportunists. These are what they call script kiddies. These are the ones that, they mostly act alone. They're using public tools and methods. They're seeking thrills or recognition. And, they may find an exploit online and they launch it at a target without really knowing the effects or the implications of it. And it may cause low to medium damage. You get down beneath that, you get more into the idealist, lone wolf, hacktivists. A decade ago, Anonymous was the hacktivist type of group that was very well known. They're not so much in the news anymore, but they'd focus on attacking systems across the world, seeking retribution and revenge for whatever political ideal or other ideal that they are trying to focus on. And they can act alone or in groups and coordinate, and that creates a problem for people trying to defend their systems. Beneath that is a little bit more sophisticated, organized cybercrime. This is where you have, contract for hire. They have teams. This is a business for a lot of nefarious groups in the world, and it's mostly financial related. The damage potential can be super widespread. This is where if you've heard the term botnets before, this is where these types of groups will compromise hundreds of thousands of devices across the world for purposes of financial gain. They will sell that access, they will use it in a specific way to get money, and it's organized in that way. The very, very bottom tier, this is where we get into the state-sponsored, like I was talking about, advanced persistent threats. And this can be associated with nations, associated with countries, and they are very sophisticated. They can be associated with military intelligence units, high degrees of skill, and their compromises can be very targeted and have significant damage. When I mentioned Volt Typhoon and them pre-positioning in critical U.S. critical infrastructure, that's where this echelon of cyber threat comes from, and they stay within systems, they hide for long periods of time for some future event. Now that requires a lot of skill, a lot of planning and coordination. So that kind of gives you the very quick progression in terms of the cyber threats that we're dealing with, so that when we build our systems, we can know the possibilities, the breadth of possible. Now, when it comes to how an actual cyber attack progresses, there's a basic cyclical process that I show here, kind of from the MITRE ATT&CK framework, which is a way to characterize various cyber techniques. And you'll see it: reconnaissance, they have to identify what they want to attack. Resource development, they have to develop the tools and techniques, the little vectors to actually get in and pre-position into the system that they're trying to attack. Then there is an initial access, whatever that is. It could be spear phishing, it could be dropping a USB in a parking lot. There's a variety of initial access techniques. Once they're in a system, though, that's where they can go wherever they want, and potentially, depending on how it actually unfolds. And this is what we do when we do red teaming and pen testing. We are going through this cyclical process, just like the real cyber threats are. And so we'll attack a particular system. We will establish persistence in that system, maybe, so that if it reboots, we can stay on that system. Maybe we'll tamper with security technologies, defense evasion. If we move laterally, that's jumping from one system or one device to another, and extending our compromise within the system. And then exfiltration is the final component sometimes, where we simulate stealing data, and that can be very relevant to the healthcare space, where patient data is, of course, what everybody's worried about, what adversaries are trying to get access to, and they leak it out to, or they steal it and put it onto their own systems. So that's generally the flow. It doesn't happen, in a sequence like that. It can jump around once you get initial access, but in general, that's what we're talking about. Now, let's talk about medical devices and systems real quick. So how this applies to you, and there we go. I drew this because the medical space is very complicated in terms of cyber threats and cyber vulnerabilities. You take, for example, the different locations at the very top: hospital, patient-facing, hospital data center, hospital offices. Those are distinct types of locations that could have different devices, different types of technologies, and those become different attack surfaces. And I also overlaid that horizontally with traditional workstations, specialty embedded devices, and traditional servers and applications. So all of those can exist in different spaces, and that becomes part of the attack equation, the attack path equation. So, and then at the very bottom, the vertical lines of different colors, red, orange, and yellow, these are the different vulnerability and threat classes also overlaid on everything else. You can have software exploitation, misconfiguration of a system or a component or software, or just normal functionality abuse. That's another class that I like to call out that we attack, because attacking systems as a cyber threat is not always using an exploit, not always attacking a piece of software vulnerability. It could be misconfigurations based on implementation, or it could just be I'm using the system against itself in a way that benefits me as the attacker. And so that's where the example attack path that I drew. This is how, unfortunately, this is how the entropy can unfold. You can start on one system in a specific location that's easier to attack, and there could be adjacencies that allow you to attack iteratively other systems and other components. Now, it's not always, 100% success where you actually penetrate all the way into a system that you're trying to get get the data or to get whatever it is that you want. But unfortunately, more often than not, the complexity of these types of systems usually allows some kind of path to get there. And that's where you got to think, the very worst of the worst cyber threats that are out there, that's what they do. They constantly think about these paths. How do I get to that point? And that's going to get into a lot of what we talk about in a second for how we build medical devices in a better way to be more resilient to those types of techniques. Now, in the IoMT space, Internet of Medical Technology things, you've heard of IoT, Internet of Things, IIoT for Industrial Internet of Things. They all kind of have similar characteristics in that they are small form factor. Most of the time, they're embedded devices, and they are network connected. And so the software stacks that are implemented on these small form factor computers and devices, Sometimes they don't have good security controls. They don't have good hygiene, regular cyber hygiene, access control, and how to get in to the systems in a secure way and operate them. And so that's what cyber threats attack on these particular devices. Now, IOMT being specifically medical technology focused, these are where we kind of get into the point of care technologies, point of care testing devices, where the small form factor specialty devices are used for patient care types of things, but they have similar characteristics. They're network connected, they connect to upstream systems, they send data upstream to various things. In this example, this is kind of the IOMT workflow that could exist out there. You have a device that needs to connect to the cloud because a lot of different medical devices nowadays, and not even just medical, industrial, other things, the goal is to get the data to a place that a lot of people can access. Well, the cloud is the natural thinking for that because it's always accessible, it's easily accessible, things like that. But you think about the architecture and the very specific components that are in these cloud types of systems, this is where you need to start considering where the threats may exist and where they lie in that entire equation. Now, some of them may not be your responsibility to protect or defend against, but as you're developing devices, developing software, think about this entire piece of the puzzle. We want to provide devices that provide good patient care, good testing and diagnostics, and the reliability of the data goes to a place unaltered, untampered with, and that whole workflow, medical staff being able to interface with the data and executing the patient care mission, that's what we want, right? So as long as we understand the whole chain of the puzzle and we work with people and try and mitigate threats, and anticipate the potential issues, that's what we want to do. So threats can exist either on the devices themselves, in these cloud gateways. You could have a threat in the control application. There could be a threat on the other side where the medical staff has the interface, the patient interface, or an admin interface. I can't tell you how many times I've attacked a system and used an administrative interface, a back-end IT type of interface for a system, and have control of the entire thing because that usually allows access to a lot of different components. So it's always the weakest link in the chain will cause a cascading effect for the entire system. So we just have to think about where our devices are in the equation of patient data going from point A to point B, and where the potential failure points are. Now, in terms of device architectures, so in the point of care technologies, point of care testing, this is how you're going to see them. And of course, if you are developing devices yourself, this is the examples that are out there for you to follow: blood gas electrolyte analyzers, blood glucose monitors, pulse oximeters, portable ultrasounds, portable molecular diagnostics. We're starting to see, kind of with the trend of general computing technologies getting smaller and faster over time, that's enabling a lot of interesting devices to be made. Now, interesting has its side effects, right? If you don't do it correctly, there could be a way that an attacker could abuse some component of the system. So you have to be very careful when you're developing these things. Naturally, that's what we deal with a lot with security in general, is vendors make technologies, make hardware, and they may not think about, how can X component within the architecture be abused? How can I adjacently attack another component of the system? And then it just kind of causes that cascading failure where at the very, very end of the chain, data is stolen or the device no longer functions or any of those final effects that are negative. But when you look at these different classes of devices in the point of care technology and testing space, think about where's the patient data stored on the device, which hardware components inside of the device actually process the data, and then where is the patient data sent, transmitted to, because naturally you see in some of these images, wireless is the new space, right? That's what we want. We want small devices that measure things, that have diagnostic capabilities, but we obviously can't consume the data, so we need to get it somewhere. Where do we get it to? Do we put it on a phone? Do we put it up in the cloud that then is accessed by a smartphone or type of tablet device? Those are all considerations. Where's the data being sent and transmitted to? And then what protocol, what network path and protocol are you actually submitting that data to? or across, because that could have huge implications on data security. Naturally, having good encryption, using things like TLS, transport layer security in the old days, secure sockets layer, SSL, using things like that, having encryption in your traffic, those are step one for getting data from point A to point B in an encrypted fashion. But in between that, the wireless communications, Bluetooth, um, some sort of ISM band, radio frequency, RF communication, those could be sniffed in the air by specialty devices. You have to think of the whole chain of encrypting communications from the actual diagnostic device up to some other device that then transports it to the cloud. It really depends on the architecture, but you kind of get the point of what I'm trying to say. Now, when we get into the devices themselves, if you're approaching the problem of I want to build a medical device, a medical testing device or diagnostic device, where do I start? What do I do? In the hardware space, you have a lot of different options. Today is a very good time to buy commercial off-the-shelf hardware because there are a whole bunch of different options. They're very fast and very capable for the size that they give you. And so you generally have, kind of the options of either single board computers. This is where you'll have, these are still embedded types of devices. They're smaller form factor. But single board computers, they'll have a central processor, a system on a chip, a SoC of some kind that can run an embedded Linux operating system or something like that. And you'll have a fully featured stack of software and capabilities that are typical of, larger types of devices. Now, you could also do, if your device needs to be super small, microcontrollers. And so the trade-off there is you'll have a smaller amount of compute power, but you'll have a lot smaller form factor. Now, the smaller compute power means that you may also have smaller capabilities for defense and monitoring, things like that. Raspberry Pi Zeros, ESP32s, they're all meant to measure sensors, measure different GPIO, general purpose IO inputs and outputs, and analog and digital signals. You can do a lot of things with these types of devices in the IoT space or IOMT space. But there are trade-offs, there are downsides to it. Now, if you're a larger scale manufacturer, you may not bother with commercial off-the-shelf boards and microcontrollers. You may just go full custom hardware, building your own PCBs. In my open source research, I found one of these Nova 13 biomedical electrolyte analyzer main control boards available on eBay. It's an older technology, but if you look at the actual printed circuit board there, it's very predictable in what they're doing. It is a central processor of some kind. You have additional integrated circuits and semiconductors laid out in a specific way. And the downside is it's cost, right? It takes a lot of time and effort to build these custom PCBs, whereas with these single board computers and microcontrollers, you could, buy them for very, very cheap, install an open source Linux operating system on them, plug in your sensors into general purpose IO, and now you potentially have a full working system. So I show you that breadth and depth a little bit, just so that we continue the conversation and thinking of where's the patient data stored on the device, which hardware components actually process it, where is it sent and transmitted to, because that becomes a very important piece of the puzzle. Now, in terms of embedded system architectures, I don't want to get too deep into the weeds of how these systems are architected, but it's important to understand where the threats may lie in a layered fashion like this. So in any of those previous hardware examples, you say at the very bottom, whatever the hardware is, single board computers, microcontrollers, they may have firmware storage. Above that, that's where you'll have some differences depending on if it's an MCU or if it's a single board computer. You could have an embedded operating system. There's just functions exactly like Linux, a real-time operating system, or in the microcontroller space, you can have a small RTOS, a real-time operating system, or it's just a main loop with functions, a main loop of code that constantly goes. Because in the microcontroller space, we're talking megahertz of clock cycles as opposed to gigahertz for more powerful systems. And maybe their purpose and their function is just sensor reads. And then on the embedded side, up above that, you'll have your software applications, and that's where you get more fully featured things that are more closer to desktop type systems. Now, I layer that up so that you can see that from the very, very bottom, there could be threats down at the firmware level, down at the firmware storage level, and those will kind of chain on top of each other depending on which hardware direction you take. And all of which, this is what makes microcontrollers, embedded devices so interesting in the device development space is they come pre-packaged with Wi-Fi, Bluetooth, sometimes 5G or 4G LTE cellular, but connectivity is baked in. A very, very small ESP32 microcontroller has Wi-Fi and Bluetooth built into it. That's great. It's great for connectivity. It's great for building things. But you got to think, what's the implementations of those software and network stacks? Are they vulnerable to anything? Sometimes we don't know, right? In the vulnerability landscape out there, it really comes down to, are there known vulnerabilities, common vulnerabilities and exposures, CVE numbers, if you're familiar with those, where security researchers will kind of talk to the vendors, they'll publish things, they'll find bugs, and then they'll publicly report them so that everybody's aware and they can download a software patch. Sometimes that's not actually done, or there's kind of a gap in coverage and somebody hasn't looked at it yet, or researcher hasn't looked at it yet, and there could be a vulnerability that exists. So it's all part of that thinking. It's good that there's connectivity there, but there could be an issue where things can be abused. And that data goes all the way up, right, to that network communications layer. If you are communicating your data up to the cloud, either through Wi-Fi in a hospital environment, Bluetooth to another device, or over cellular up to the cloud directly, AWS, Azure, um, all of this technology is very quick and great to put together, but there's a lot of implications, a lot of touch points, a lot of things that touch each other that could be abused. So it's just have consideration of where these types of threats may lie. Now, at the very, very bottom, though, hardware and firmware storage, this can become an issue. And without getting into too much detail, but at GTRI, we have embedded systems research, and firmware extraction and exploitation is a big piece of that. So when you're talking about a hardware board in general, an embedded device, microcontroller, there could be a situation where there is a storage chip, a flash read-only memory of some kind that is also on the board that stores the firmware. And the firmware could be where the main OS actually starts launching once the device boots up. Now, where it becomes interesting and important for defense is when you're developing these devices, you have to assume that someone will break it open and reverse engineer it. And how they reverse engineer it will be through methods like this, where they find that flash chip and hook basically these alligator clips to it, boot it up, and pull the firmware image off. Now, once you have the firmware of a embedded device like this, you can do a lot of things. You can implant backdoors and then reload it, reflash it onto the flash chip. You can modify the firmware. And so it becomes concerning. And this is my cautionary tale of when we get down to the firmware level, this is where we have to have obfuscated, encrypted firmware so that when the device is broken open and pulled off, you can't actually do anything with it. It won't load, different mitigations like that. So you have to have mitigations across those different echelons, across those different layers that I mentioned. But this becomes a very important piece because it is the source, it is the bottom root of trust effectively for the device. If the firmware itself is compromised, either from the factory in a software supply chain compromise pipeline, or someone breaks it open, extracts it, reflashes it, those can all be threats to everything above that. So to give you that quick overview of threats and issues in the IoMT and point of care technology space, what do we do about it, right? So we only have an hour to talk about this, but we're always available as researchers as well to partner with you on your projects to help with these sorts of issues. So if you're a medical device developer and you need a place to start. You need to know where to go from here. The first place that I always start is, let's start at the top. Federal laws. What do the laws actually require me to do? So looking, a little bit at the FDA's website, it pointed you to the omnibus. The Consolidated Appropriations Act, aka Omnibus, was signed into law back in 2023. And so when you look at that bill at the federal law level, it just says cybersecurity requirements for, when you submit an application, it needs to address, have a plan to address cybersecurity vulnerabilities, exploits, and disclosure processes. And you have to design, develop, and maintain processes, procedures to keep a system cyber secure. And after post-market, you need to have updates and patches for vulnerabilities that may come out and different cycles, things like that. I say all this to say this is usually what you'll see at the federal law level or any kind of regulation. It's very broad, very generically written so that it covers a lot of edge cases. It's basically saying you have to have a plan, right? And that doesn't tell you very much as a medical device developer. What do I do? What do I have to actually implement to satisfy these types of things? And so that's where you dig a little bit deeper and go into the FDA's requirements themselves. Now, on the FDA's website, cybersecurity of medical devices quality system considerations and content of pre-market submissions. This is, you've developed a device and now you need to get it approved and accredited by FDA. This is the document that you can follow. Now, these are non-binding recommendations, as their website says, and I'm definitely not an FDA device expert, FDA requirements expert, but this matches a lot of requirements that I have to deal with on the DoD side and cybersecurity requirements. Whoa. I didn't like that. Hold on. There. So when you look at this document, it's about 64 pages long. I recommend you look at it yourselves if you're in this issue. But I pulled out a couple of pieces here. General principles. Cybersecurity is a part of device safety and a quality system regulation. So the overarching narrative that they have in this is building a quality system, a QS, and the QS regulation. So one of the big things that they call out is a secure product development framework, an SPDF, may be one way to satisfy the QS regulation. And within that, using an SPDF to manage cybersecurity risks, this is the main body of the types of things that need to be done for your system, for your device, to be able to have that quality system. So security risk management, security architecture, cybersecurity testing, and it includes things like threat modeling, which is, identifying all the attack paths, playing the role of the adversary on paper, and identifying where your system may have issues, conducting a risk assessment of your entire system architecture, interoperability considerations, where your device actually interfaces with other things. If you need to hook to an EHR system or something else in the medical environment, there are considerations for how, data is exchanged and how you connect to things. And then, in the security architecture side, implementing security controls. If you identify that something could be abused in your system, what are the controls that you have that prevent it from actually escalating to the point of exploitation? Now, cybersecurity testing, this is where it kind of gets into our area of expertise and research. This is where we have threat mitigation, vulnerability testing, and penetration testing. And so we actually go through the exercises of take a system as is and its current state. Let's look at all of the pathways that we can get into the system as an attacker. Once we get into the system, how do we move around within the system? Where is the data stored? Can I get access to the data? We go through all those questions iteratively in our process. And as part of that vulnerability testing and penetration testing, we provide, the report of this is what we found. These are the mitigations that we recommend you implement, things like that. So you see in at a high level, FDA and everybody, they want you to have a plan. They want you to have all of these different steps and procedures to mitigate the risk as much as possible and involve third parties, right? That's what you have to do when you get vulnerability testing, threat modeling, penetration testing. You really need to get a third party that specializes in this to look at these types of things. And that's what we do. Of course, we can partner with you on research projects. I'll get into that at the very end of this and how we engage. But One of those pieces for developing a quality system as the FDA wants, and understanding where your risks lie in the system architecture, I point you to these resources from CISA, the Cybersecurity Infrastructure and Security Agency. They're really taking a big effort right now to make themselves America's cyber defense agency. And part of that is education and awareness, getting software developers, hardware developers, system developers to understand and document where their risks may lie. So, as part of those FDA requirements, an HBOM, a hardware bill of materials, and an SBOM, a software bill of materials, are called out. And those are good paper exercises for documenting how is your system architected, what are the specific components in them, where are they sourced from, where did they come from? Because the issue nowadays, one of the primary attack vectors that a lot of cyber threats use is software and hardware supply chain compromises. They attack the source and implement or inject their malicious logic into hardware, into software, so that it immediately just gets installed into the system that they're interested in. And that kind of subverts and bypasses all of the efforts to try and penetrate that organization from the outside. So it's been used in the past. There have been high profile software supply chain compromises they're coordinated with cyber attacks in the past few years. They've been pretty damaging. So CISA is taking the approach of awareness education. This is how we recommend that you stop these types of things. And it's really documentation, figuring out everything that is interconnected within your system. That kind of gets into this piece, secure by design. It's another push that CISA has, where your system is the responsibility of mitigating risk is kind of pushed back on the manufacturers of either software or hardware. It shouldn't all be on the people who implement the technologies to defend them, because they can't control some of that sometimes. So this education campaign is to push device developers, system developers, software manufacturers. This is how you build secure code. This is how you build secure hardware devices. So I recommend you take a look at these types of resources. Search Google for Secure by Design from CISA and hardware and software bill of materials to get an idea of what they're recommending. Now, the final piece that I'll mention is if you're developing web applications specifically, or you have a web application that's part of your process, either from your medical device that needs to be sending data to a web app that you build. OWASP, the Open Web Application Security Project, is great for tracking and providing recommendations for different classes of vulnerabilities. Web application security is a is a career field in and of itself. And it can be very complicated depending on how complex your web application is, but they're a primary target for cyber threats. And so take a look at OWASP and their top 10 types of vulnerability bugs, and make sure that your web application, follows those types of recommendations to prevent exploitation. So, I mentioned that this is a very fast and high level overview of a lot of different topics. Certainly, we can dive deeper into some of these others in the future. But your main questions are, how do I secure my devices? How do I approach securing my devices? How do I engage with experts on the outside if I don't have cybersecurity expertise in my own organization? We're here to help. We're a not-for-profit entity. We're not in this for money. We're in this for solving problems and to prevent cyber threats from attacking our systems. So you can collaborate with us either from existing ACME projects and funding. We can partner together on new grants. If you want, we can provide independent consultation and assessments. I mentioned all of our funding is external, so we have contracting entities at GTRI to provide specialized testing services agreements. Custom contracts to provide that independent third-party assessment of your system, cyber assessment of your system or your architectures. And then also I mentioned training. If you need training for either you or your employees at the organization that you work for on how to build secure embedded devices, how to attack them, how to defend them, we've got courses already in the pipeline, already part of our certificate program. You can go to GTPE's website or contact me directly. So I'll leave it at that and let's do a Q&A session. Here's my contact information if you need it.
Thank you, Dr. Lewis. Um, Such a ton of information in such a short period of time.
Yep.
Um, when we reviewed this, I loved going through the OWASP things, actually. I really feel like I learned a lot about software design as it relates to security.
Hmm.
So this is the Q&A portion of the webinar. So if you've got a question, feel free to drop it in the Q&A tool panel thing at the bottom of your Zoom, and we will answer those as we go. And I'll get us kicked off here. You know, tell me a little bit about some of the biggest or the most common security challenges that you see in the healthcare space. And if you go down to the point of care space, that's even better. But what are you seeing from just a general healthcare space in terms of the biggest challenges and risks?
It becomes entropy and complexity, and I see that in a lot of different industry sectors as well. As technologies progress, as vendor solutions progress, the number of devices and applications that are being installed in these systems gets to the point that it becomes untenable to really track and mitigate vulnerabilities. Because there's not that good hygiene coming from where these systems and software are being developed. Unfortunately there are vulnerabilities built in constantly from the factory, and so then you take a healthcare operator and they build in a technology. They don't know if there's vulnerabilities in them or not. And so, depending on how the system is architected, there could be a vector, a pathway in, and then they're always behind the game. That becomes the issue for defense and operations. Once a system is attacked and compromised, you're trying to play catch up to figure out where was the attack, how bad is it, where do I go from here? And unfortunately, sometimes the adversary has the edge, and they can always stay one step ahead. So, in my view, the number and types of technologies that are being installed in environments, hospital environments, um, really amplifies both sides in negative ways for us trying to defend systems, and positive ways for attackers.
Got it. I think about point of care companies, particularly small companies, they've got two enormous hurdles. The first is the FDA, which of course you mentioned. Um, but the second is once they're authorized, getting those first few customers to
Mhm.
say yes and to work with systems. And I've tried a few times to work with hospital IT to get things in, and it can be quite challenging.
Mhm.
You talked a little bit about um, the complexity of the problem for those administrators. Is there anything that developers can do to make that easier? Is there an easy button? Is there like a certain certification or a certain, set of things that you've already done as a developer to make that integration even easier for the hospital system?
Yeah, I don't think it's not necessarily an easy process. It is an easy button, and I would say it's getting the narrative correct. So if you go to a hospital IT person and you're speaking the language, you're saying that I covered all of these things as per CISA Secure by Design, or as per all these things, and you're actually on the same page with what the threats, what the risks and concerns are, it becomes a lot easier for them to implement. The example that I have is not in the healthcare space at all, but in the electric power and energy space. One of our research projects is we're building small form factor embedded devices to be plugged into power systems to prevent cyber attacks. And I'm dealing with that as well, going to power utility operators. They look at me and say, "You want to plug in one of your devices into my system that I'm relying on to control power?" And admittedly, it's a very concerning thing. So I've had to go through that cycle myself and say, well, I'm designing the system in a very specific way so that it can't be attacked. And I'm also designing it in a way that it can't be used to attack your system. And so little bits, little details like that, those are the things that shine. And I think in our world of, cyber education, hospital IT, they're in it just like we are. And so we're kind of all dealing with this how do we secure things together. So if you can interface on that type of level, I think it'll be a lot easier to get them to adopt your technologies and install them.
Cool, great. One question from the audience here is about Wi-Fi,
Mhm.
which is you talked about Wi-Fi communication vulnerability. Can you expand on that? Notably, if data is the only thing being pushed, how siloed is the device from being a weak link in the overall architecture?
Okay. Yeah. I mean, if you're doing good things like, you're encrypting your traffic being sent over Wi-Fi, naturally, if you build a medical care device, point of care testing device, it needs to connect to hospital IT or, whatever medical environment IT. You can't really control as the device developer how they implemented their Wi-Fi stack. Is it, or their Wi-Fi devices? Are they attack surfaces themselves? Yes, they could be. But as long as you and your device, you are implementing good hygiene in your traffic, you're encrypting your network traffic to use their Wi-Fi network as a transport mechanism, then your device becomes in a better position, a better posture. Now, in terms of like Wi-Fi implementation, Wi-Fi stack in your device, there could always be issues and vulnerabilities with your device's Wi-Fi stack. And that could be from the factory. It could be something that you don't know, right? So keeping abreast with those types of issues. There is open source information out there. There have been chipset level Wi-Fi types of vulnerabilities. And it's basically, the RF signals that come off of the Wi-Fi cause the microcontrollers, cause the transceivers themselves to misinterpret data, and you could get an exploitation vector that way on your device inbound. And so then it becomes, some of that you can't control, but just keeping up with the firmware of your Wi-Fi transceivers, keeping abreast with the open source community and whether or not vulnerabilities have been identified in those, using transceivers, using Wi-Fi chipsets that are well known. Those are the things that you can do to kind of better posture your device from attack from another system.
Great. So I have to mention when you shared your deck with me, I noticed that Box would not allow me to look at it until I had set up two-factor authentication. So you sort of practice what you preach in terms of
Yeah.
security.
Yeah.
Pretty rare that I have to do that to access a file. And I guess for those of us who are not security experts, what's kind of one practical takeaway that we can implement both when we're developing new software and tools, but even just in our daily lives?
Yeah, I mean, two-factor authentication is great. How it's done is kind of your mileage may vary in terms of security. We use Duo at Georgia Tech, and the way that we do it, it's a push to your phone, but you have to enter in a code. And so some two-factor technologies are easier to subvert than others. The push notifications to your phone are a great thing. But if, say, you're an attacker and you've compromised somebody's account, you can push constantly and the user gets fatigue. And so they think that it's part of the authentication that I did previously, and they'll just allow it. And so you can trick a user to get into that mode of allowing a two-factor authentication. So that's the game the attackers play. So you have to be careful with which type of two-factor authentication you use. Certainly the codes, the one-time pins, those kinds of things from your devices, those are generally proven secure. So yeah, in answer to your question, what can we do? It's a lot of the basic cyber hygiene things, good access control, like two-factor authentication, strong passwords, strong encryption for your devices. Those are the big pieces of creating a secure system.
Awesome. Well, I think we'll end it there. Angie put a link to an evaluation. Just takes 1 minute, I think. If attendees could fill it out, it helps us make these glue sessions better and better. And thank you, Trevor. Thank you, Dr. Lewis, for
Yep.
speaking to us today. And we'll close the webinar there.
Thank you, everyone.
Thanks. Bye-bye.